Okay, we're going to go start it here. When actually, okay, might need a new battery, which I believe I have. Okay, so we've moved on to light, and we talked about reflection and refraction. Um, this is, you don't have to write this down, just here's a little summary. So, um, I guess in about 1000 AD, it was proposed that light consists of tiny particles. And Newton also believed the particle theory of light. And he used this particle model to explain reflection and refraction. We kind of do the same thing nowadays when we talk about ray optics. We're treating it as a particle that moves in straight lines and bounces off. This guy Huygens in 1678 explained many of the properties of light by proposing that light was wave-like. And then this guy named Young in 1801 did some experiments with slits to show that, um, which supported Huygens' theory of light behaving as a wave, because he was able to show the interference patterns associated with light. And then Maxwell came in 1865 and demonstrated that light was an electromagnetic wave. So there were a lot of things that supported the fact that light was a wave, but there are also a lot of things that are not explainable by waves, like why does light get absorbed in quanta? There's a certain um, like it's packets of energy, but it has both wave and particle-like behavior, and we just have to accept that. You can't say it's one or the other. It actually is both of them. Now Einstein, um, he investigated certain things that would indicate that it acts like a particle. One is this thing called the photoelectric effect, and that's where electrons can be liberated from the outer shell of a molecule if light of a certain frequency is incident upon that surface. But if the frequency isn't high enough, then it doesn't matter how intense the light is or how intense the electromagnetic wave is, the electron is not liberated. And that is more of a particle type thing. And then this guy named Max Planck came up with ideas of why the changes in the electrons from different energy levels within the molecular structure result in light of different wavelengths. So it explained spectrophotometry associated with chemistry. And because these wavelengths or this energy was quantized, again, would indicate that it has some particle nature to it. So there's a lot of um, different things that support those two theories. Ultimately, they came down to the fact that it behaves as both. Okay, so now we talked about ray optics. There, we just treat it as a light going in a straight line, and it hits a surface, and either it is reflected or it refracts. One thing we haven't, well, we talked about this previously, is we have this relationship between wave speed, frequency, and wavelength, and it's the same relationship we dealt with when we talked about sound, except instead of the sound the speed of the wave being the speed of sound, it's the speed of light. And so the speed of light is equal to the frequency of the light wave times its wavelength, which obviously has to do with the wave behavior. And I did remember to push the record button. Okay. So the only thing that we've replaced is V with C. Okay, so we talked about reflection. There's two types of reflection. One is specular reflection and one is diffuse reflection. So specular reflection is the kind that we think about. It's a very shiny surface. So we'll say shiny surface. And the light comes in. Let's say it's all in one plane and it bounces off. And so we get, this is the kind of reflection, like I said, we're used to thinking of when we think of something being reflected. So all of the energy that comes in is bounced off. It's kind of in contrast to this diffuse reflection. What happens there is you have light come into a surface, and instead of going off at a particular angle, it goes off in all different angles. Okay. So that's what diffuse reflection means. It's kind of like if you look at a non-shiny surface. I mean, there's two things you're getting here. One is just the color of the object, which is not reflection. There, the energy is being absorbed by the molecules and then being re-emitted. And so it's an absorption thing. But here it's just the difference between a shiny surface and a non-shiny surface, basically. We're going to be dealing with specular reflection because that's the one that gives us mirrors. Okay, we talked about the reflection, refraction. Yeah, the question is, what happens to the wavelength and frequency of light during the transition from one medium to another? So let me turn this thing off again. Okay, so what we had right at the end of the class is we had some boundary between two surfaces with different indexes of refraction. And we had the light ray coming in at some angle. And if we drew a normal to the surface, the angle between the normal and the incident ray was called our angle of incidence. And if the index of refraction of the transparent material was greater, then it bent towards the normal. So this was our angle of incidence, theta sub I. This was theta sub R, angle of refraction. So as the light comes in, it slows down because the speed of light through something that's not a vacuum is going to be less than 3 times 10 to the 8th meters per second. So which one of these two things would change as you go through the interface? Well, the frequency is not going to change because of the periodic nature of it. If you've got waves coming in, and if they frequency change, you'd have to change the, it makes more sense that the wavelength is what actually changes. And you can see from the relationship between speed and wave speed, which in this case, what we're doing here is we have the speed of light in the original one, which we're assuming to be a vacuum because it has an index of refraction of 1. And it's going to be lambda 1 times F1. And then you're going to have C2 is equal to lambda 2 times F2. So if C2 is less than C1, which it is because the index of refraction is higher, one of these is going to have to change. If one goes up, the other one has to, well, actually, yeah, if the speed of light goes down, then either the wavelength has to get shorter or the frequency has to get less. So the answer is the frequency stays the same. So lambda 2 has to be less than lambda 1. And that's actually how you can ultimately relate the geometry. That's one way of relating the Snell's law, is to use this fact that the wavelength gets shorter as it goes into the transparent medium that has a lower speed of light. Okay, so we talked about index of refraction. That was the ratio of the speed of light in a vacuum to the speed of light in some other medium. So we don't need to do that. We were talking about diamonds has the highest index of refraction. And we looked at Snell's law, which says N1 sine of theta 1 equals N2 sine of theta 2. So typically you're given 3 out of the 4 things. A lot of times you calculate, you're trying to figure out what theta 1 or theta 2 is. And so you solve for the sine of theta 1 and take the inverse sine, and you solve for the sine of theta 2 and solve for theta 2. Or if you didn't know the index of refraction of the material, you could just measure these angles and figure out what the index of refraction is. Now, different materials have different indexes of refraction, but they also have different indexes of refraction at different frequencies. So, or wavelengths, sorry. So, that's why a prism works, is because the lights of different frequencies get bent different amounts. If you bend them twice in the same direction through a prism, then you can separate out the white light, which consists of all the different colors, into its constituent colors. So these are showing 3 transparent materials: fused quartz, acrylic, crown glass. Crown glass is something that I think you use for things like crystal. So you're trying to make something that has as much brilliance to it as possible. So they probably figured out how to make glass with the highest index of refraction. But all of them have this relationship that the index of refraction is different depending upon the wavelength of the light, the type of light that we're talking about, the color of the light. I'm going to skip dispersion right now. So here's a prism. So the white light comes in. This is going straight through. If the angle of incidence equals the angle of refraction, then you would go straight through. But what actually, let me draw a normal here. So here's the normal to the surface, and they've kind of they've exaggerated as a consequence. They've exaggerated the blue. What these represent are just the angles after you've gone through 2 surfaces. This is not refraction. This is red and blue. Okay. So what they're doing is they're just talking about the difference in the angle these 2 lights make with each other, how spread out they get. And when you observe this with your eyeball, you'll see that they're not in the same location, and they get refracted out. But yeah, so they've exaggerated. Probably shouldn't have drawn this line because it illustrates they went a little too crazy with their refraction. But what happens is, as you go through here from the essentially a vacuum or air, you're going to bend towards the normal. And then if you go out, if I now go out this way and I draw a normal to the surface here, it's going to bend away from the normal. and this one bends more. This one bends more towards the normal, and again, if you draw a normal line out here, that one bends more away from the normal, and as a consequence, both of those straight surfaces at angles accentuate the amount that the light of different colors gets bent away from each other. And I guess that's, let me, we looked over here at refraction somewhere. Now, if you go the other direction, so before we talk about, let me draw a line here. So let's say we're going from N1 equals 1.4 to N2 equals 1.0. So instead of going from a material of lower index of refraction to a higher index of refraction, let's say we're in a material of high index of refraction, and we come in like this to the surface, and then you draw a normal to the surface both directions. What'll happen is that instead of bending towards the normal, you actually bend away from the normal like that. And because the light's coming in from this side and going out this side, this is my angle theta sub I. That's my angle of incidence. Let's say theta sub I equals 50 degrees. The question is, what is my angle of refraction? Theta sub R. Question mark. Okay, so we use Snell's law just like we've done before. We say N1 sine of theta 1 is equal to N2 times the sine of theta 2. So it doesn't matter which direction we're going as far as this law. We just have to be consistent with our subscripts. So we get the sine of theta 2 is equal to N1 sine of theta 1 divided by N2. So the sine of theta 2 is equal to N1, which is 1.4, times the sine of theta 1, which is 50 degrees, divided by N2, which is 1. So we get our calculator out for that. Make sure our calculator's in degrees. Okay, so mine is sine of 50 degrees equals 0.766 times 1.4, and we get the sine of theta 2 equals 1.072. Okay, is that a problem? If you try to take the inverse sine of 1.072, what will your calculator say? You can try it. Inverse sine of 1.072. It says error. Okay. Obviously, I haven't drawn this to scale. So what's going on here? Let's try a different combination. Let's come at a smaller angle. Let's let theta 1 equal 20 degrees. Let's try that. So the sine of theta 2 is going to be 1.4 times the sine of 20 degrees divided by 1.0. So the sine of theta 2 equals, let's try that in the calculator. So you get 1.4 times the sine of 20 is 0.479. So that one is between, so if I did the inverse sine of that, I will get a number. .4788. I get 28.6 degrees. So in that case, if I look at the geometry, I'm coming in here at 20 degrees. I'm leaving it a slightly larger angle. So this is 20, this is 28. There must be, so in this case, what's happening is that instead of coming in at what's going to happen is if I keep increasing the angle and this thing keeps bending more towards the surface, there's going to be some point where that thing goes directly 90 degrees. So let's see what the answer, let's see what theta 1 would be. For theta 2 equal to 90 degrees, what is theta 1? So the question is, given n1 equals 1.4, n2 is equal to 1, and theta 2 equals 90 degrees, what is theta 1 under those circumstances? So we'd have n1 sine of theta 1 equals n2 sine of theta 2. So I'm going to solve for the sine of theta 1. So n2 is 1.2. The sine of 90 degrees, which is 1, divided by, n2 is actually 1, not 1.4. It's the other way around. 1.0 over 1.4. So if I solve for sine of theta 1, I get n2 sine theta 2 over n1. So the sine of theta 1 is equal to 1 divided by 1.4, which is 0.714. So let's find theta 1. Theta 1 equals the inverse sine of 0.714. So I get 45.6 degrees. So it's saying that if I continue to increase this angle from 20 degrees, this thing's going to get closer and closer to bending completely horizontal. And that's the biggest angle that I can have this light come in, that it actually will refract and emerge from the other side. So what we can say is for n1 equals 1.4 and n2 equals to 1, we will have total internal reflection if theta 1 is greater than 45.6 degrees. Okay? So that's, going the other direction. If you go from a low index of refraction to a higher index of refraction, the light ray is always going to be bent in towards the normal. But if you're going the other direction, if you're going from inside something, like inside a diamond or anything, and you have light inside there and it tries to escape, if that angle between the light ray and the surface is greater, the normal to that surface is greater than 45.6 degrees, for those two values of the index of refraction, the light's not going to refract at all. It's just going to bounce off internally, and then it'll run into the next surface. And if that angle is greater than 45.6 degrees, it keeps reflecting. So that's the whole idea why optical fibers work. If you have a fiber of glass that's made out of a high enough index of refraction, and you send a light ray like a laser that goes through here, the light ray is going to come here, but because this angle is greater than the critical angle for internal reflection, it's going to reflect itself internally perfectly. And then it's going to continue along here until it hits the other surface, if it gets that far, and then it'll reflect itself back in there. It'll just keep bouncing back and forth, and it will continue on as long as this curvature is small enough. just so that if this angle between the normal to the surface and the light ray is large enough, it's going to keep bouncing back and forth, and you can keep the light contained within that filament of optical fiber. So this angle here is called the critical angle, and that's how you calculate it. And the bigger the index of refraction is of the fiber or whatever your diamond, the more light is going to be trapped inside that, and then it's going to come out at certain locations, and it's going to give you that like brilliance. Instead of just giving you a boring average light, it's going to give you a lot of light in particular places on your ring, and it looks like it's sparkling. Okay, that's the whole idea. You got places with lots of light and places with not a lot of light, and as you move your ring around, you get different ones doing it, and it gives you that sparkly effect. So. Okay, this graph shows you the light makeup of different types of lamps. So you probably notice, if you buy light bulbs, there's white, there's a kind of soft white, and there's blue white, and it all depends upon the type of how you're generating that light. Whether you're using incandescent bulbs, which is the old kind of bulbs we don't use that much anymore, with a hot wire. If you're using fluorescent lights, if you're using LED lights, all those have different characteristics. Now, sunlight is more of a constant or fairly uniform distribution of the different colors, and all those colors together give us sunlight. So that's why when we put sunlight through a prism, we get a fairly continuous rainbow. But artificial light, like fluorescent light, is not a even distribution. What you end up with is spikes at certain frequencies. So we've got a frequency here in the blue spectrum. It's not spread across the blue spectrum, but it's just a spike. But it's enough of, we have enough of each color so that it doesn't appear to be just one color. If it was all blue light, it would look like a blue light. If you think about these high pressure sodium lamps, those are the ones that are used out in parking lots a lot of times. When we used to fly into Europe, they used a lot of these in their street lamps, and everything would have this orangey yellow glow to them. And you could see why, because most of their energy is in the yellow, orange, red part of the spectrum. So this is one thing if you work for a paper company. They have white paper, or if you work for a paint company and you're looking at different light, you're looking at different shades of white. They accentuate different colors in the spectrum. And they actually have equipment that gives you a specific illumination, a spreading out. They use different combinations of different types of lights to try to simulate daylight. D65 is daylight. D stands for daylight. So, light is not just one color. It's a lot of different ones. And the whole idea of a rainbow is that you have sunlight coming in at sun's coming down from the sun. It's so far away that it essentially is like parallel rays of light, and as it goes through a raindrop, it gets refracted just like a lens or like a prism, and you get this internal reflection off the inside of the raindrop. So here it's internally reflected, and then it's refracted, and so just like a prism, it separates the lights, and you always get the red at the bottom and the violet at the top. So if you're drawing a rainbow, make sure you draw it the right way. Red should always be at the bottom, or it's not a real rainbow. Okay, so talked about that, and that's it for chapter 22. Okay, we're done. So there's not many problems in chapter 22, so go ahead and we'll soon sign those for a week from today. Basically, it's some reflection, refraction critical angle type calculations. So I've given you a handout. Hopefully I gave everybody a handout. I'm also going to give everybody a ruler because we're going to draw some pictures. When you're finished with them after class, please bring them up front. Two, three, 5. Okay. So what we're going to talk about now is using the laws of reflection or refraction to describe how mirrors and lenses work. So I'm going to talk a little bit about it. We're not going to draw yet, but we will shortly. So we're talking about lenses and mirrors. Okay, so in all of these sketches and calculations we're going to do, we're going to talk about what's an object and what's an image. Okay, the object is some, so the object is what I'm looking at. Okay, it's a thing. And the image, we can typically, to create an image, you have to have something that you're focusing the image on. So in our case, the object, say the projector, the object is the little CCD display inside the projector. The lens obviously is the lens that's attached to the projector, and this is the image. Okay? If you had a camera, the camera would be the thing you're taking the picture of. The image would be what's on your film. So it's, if you had, let's think of another example. With your eyeball, the object is what you're looking at. The image is what's focused on your retina inside your eyeball. So I don't want to say it's the thing we're looking at because you can have an image without personally looking at it. So we use the letter O to represent object. We use the letter I to represent image. Once we get into drawing these diagrams, you'll understand what they are. I'm not going to go into a technical definition of object and image, but okay. Now magnification is basically the difference in size of the object and image. And what we use the difference by looking at it at a ratio. So we're not going to take one size and subtract the other. We're going to compare the relative magnitude of the two by a ratio. So if the image, so we'll say the magnification is equal to the size of the image divided by the size of the object. So again, using things that we're familiar with, in the case of a projector, the image is a lot bigger than the object that's inside the projector. So we would have a positive magnification in the case of a projector. If you have a camera, taking a picture of me, I'm the object. The image is this big, or however big your phone is these days, the image is somewhere in here. It's very small. Okay, so the magnification would be a fraction. It would be a small number. It's going to be a fraction, less between 0 and 1. Okay, so that's the magnification. So in terms of difference, it's the ratio of the sizes. Okay, then there's this other thing called real images, and I've got to remember the other one. Real and not, it's not fake. Virtual. Okay, so there's two kinds of images. So I'm going to use an example here again. So this is a real image. Okay, it's projected on a screen, and we're seeing the image not because we're seeing the image because the light is focused on this screen. It absorbs the energy associated with that image, and then it re-emits it to your eyeball, which then creates. So for our eyeballs, this is the object, and the image is inside my eyes on the retina. Okay, but as far as these two things, the projector and the screen, this is the image, and the object is up there. Now, so what is a virtual image? Well, a mirror is a virtual image. When you see something in a mirror, you're not really there. You see, it looks like something is there. You're looking at the mirror, and you see this object that's the same distance from the mirror to you, behind the mirror, but there's not actually, you can't put a screen 4 feet behind the mirror and see you can't project it on that. So images, real images, you can project on a screen or some kind of solid surface, whereas a virtual image, you're not projecting it on it, but you still see it. The way virtual images work is the light rays, say a mirror, the light rays will bounce off of the mirror into your eye, and your eye perceives the image behind the mirror. So there's real and virtual images, and depending upon where the objects are relative to the lenses or mirrors, you get either a real or a virtual image. So another example of a virtual image is magnifying glass. So you do a magnifying glass, what you're seeing through that lens, your eyeball is seeing a virtual image. And you're like, yeah, but there's a real thing behind there. That's true. But the actual image to us appears behind the lens, but it appears bigger, and it also, from our perspective, appears further away so that we can focus on the image. So that gets a little hazy because you think, oh, there is something I can see, but the actual thing you're seeing is not the object. You're seeing a virtual representation of that image. So again, once we get working on this, you'll understand that a little bit better. So what we're going to do is we're going to start with a mirror. So let me take some of these lines off so it's not too confusing here to start with. Actually, I think we'll start with the curved mirror because sometimes I think the flat mirror is harder to understand than the curved mirror. So what I'm going to do is I'm going to add a page. And that's what you've got. Your sheet is a curved mirror. And what I'm going to do is I'm going to describe the technique for doing this, and then once we do a few of them, you'll understand the process. So the way I'm going to do this is I'm going to draw this. This is just so I can make it look like your sheet of paper, and then I have to hide half of it by doing this. So let me hold on just a second. I need to make this white. I need to fill it with white. And let's see if that does it or not. Yeah, there we go. Okay. So what I have, this is a mirror. Now don't start writing on your paper yet because I want to go through some rules here about mirrors. So there's a line, a horizontal line that comes out from the mirror, and this is called the axis. Oh, did I not give any? Sorry. This is the axis of the mirror. So it's like the center point of the mirror. So I have a curved mirror, and what I want to look at is how the object. I'm going to put something in front of this mirror. Now it's not going to look like a flat mirror because it's curved, but you can think of, again, you can think of a flat mirror. Let's just think of it as a flat mirror for a second in terms of what's going on here. Is you're going to have the thing in front of the mirror, the real person in front of the mirror is your object. So I'm going to show the object as an arrow. And we show the object, and we just show it one side of the center line. So we usually show it pointing up, but it could be pointing down, doesn't matter. But we show an arrow, and this is, we'll use an O to stand for the object. That's why I told you what O stood for. So this is the object. And what's happening is, so let's think of this as being the object. What is going on here? Well, each point on this object is emitting light of a different color, depending upon the textbook, and it's going off in all directions. And all those rays of light are just going out, and they'll keep going out until they run into something, either a shiny surface like a mirror or a lens like glasses. Okay. Once they see that surface, then they'll be either reflected or refracted. Now what happens with the mirrors is the light rays will go, let's just look at the end of this object. So we're just looking at this one point on the object. And so the light rays will come in here and they will bounce off of the mirror. And they'll all be reflected according to the laws of reflection. The laws of reflection says it says you draw a normal to the surface, and the angle of incidence equals the angle of reflection. So all of these have normals to them, right, like this. So they're all going to bounce off at different angles. And then they're going to come back in the direction that the object is. And they're going to be all crossing all over crazy directions, but there is going to be some point, if this is a spherical mirror, where all these rays from here are going to come back together into one point, and that's the focal. That's where the image is going to be focused. Now, with all these different rays, it would get very confusing. So we limit ourselves to a few specific rays. So we're going to look at a ray that goes parallel to the axis of the mirror. That's one ray. Now, let me just diverge here 1 second before we continue on here. If you have parallel rays of light coming in, so now instead of the light rays going out in all directions, you have parallel rays of light coming in, like from the sun, what will happen is all of those light rays will reflect and go through a specific point. And this point here is called the focus. So you can, lenses, if you take a lens, like a magnifying glass, and you put it out in the sun, and you move it back and forth, there'll be some point where all the light rays are concentrated. How many people have done that with a magnifying glass with the sun? Anybody done that? Okay, so if you take a magnifying glass and you put it out in the sun, they will all the light will be concentrated at a particular distance. It'll be concentrated at a particular point. You could catch something on fire by doing that. Okay, and the same thing's true for a mirror. Not all mirrors, they have to be a specific shape, but for spherical mirrors, so it's the shape of a sphere, like a circle. All the light rays that come in parallel are going to be bounced off and go through a particular point called the focal length. Okay, so that's one thing. Okay, so let's just write that fact down. So light rays parallel to the mirror axis reflect through the focus, or at the focal length of the mirrors. So that's one thing we're going to use. Secondly, if you have this object and the specific light ray that comes out here, can go any direction. The one that goes through the focus reflects parallel to the axis of the mirror. So that's number one here. Light rays parallel to the mirror axis reflect through the focus, or at the focal length of the mirror. Number two is light rays that pass through the focal point, I'll just call it focal point focus, through the focal point, reflect parallel to the mirror axis. So if I have a point in the middle of this little arrow, it'll go through. If it goes the ray that goes through the focal point will bounce off the mirror and go parallel. If they're parallel, they go through the focal point. If they go through the focal point, they reflect off and go parallel. So that's kind of the second rule of mirrors. The third one, if this is a spherical mirror, then what happens is a light ray that comes in and goes right to the center of the mirror. You can see at that point, this is flat. If you draw the tangent line, if you drew the normal to this surface, it would be the axis of the mirror. So in this case, this angle into the center of the mirror bounces off, and it's the same angle it reflects at. So the third rule for mirrors is light rays that bounce off of the center of the mirror have equal angles relative to the mirror axis. So let's we actually only have to use two of these rules to be able to predict what'll happen with this object, where it will focus the image. So I'm going to say the focal point is right here. Oh, it sounded windy out there. Okay, so what we're going to do is we're going to draw a line from the tip of the object parallel to the mirror, and we're going to bounce it off through the focus. So you can draw that on your first. So now you can draw that. I'm not sure if it's going the other direction, but and you'll see there's two little marks here. So you just have to invert it in your brain here. So draw. Well, I guess we could do it this way. No, yeah, actually this way. Yeah, it just depends on the way you hold this thing. So let's hold it so that it has the same orientation that I have. Place the object outside of the two marks. I'll tell you what the two marks here are in a second. So if you draw a little arrow sticking up about right here, and then draw one line that goes parallel, use your ruler to make a parallel line, and go through the first mark. So the first mark here is the focal length. The second mark is actually the center of the mirror. So the second mark is the center. Bounce off and go through the first mark. So let me just put some marks on here so it looks kind of like what you've got. So this would be your first mark, and this would be your second mark. Put a little F right here, and put a little C right there. F stands for focal length. C stands for the center. Draw a line to the left of the center. Then draw, and this line here has an arrow on it. Then draw a line parallel to the axis, which I show you there. Have it bounce off and go through the first mark. And you have to continue this on far enough. Okay. So that's the first thing. The second thing you do is you draw a line from the same point on the object, and you go through the focal point this direction. So go ahead and do that. So you'll have 2 points. The end of the arrow that you drew, the focal length. So draw then the line through there. That line will then intersect the mirror. It will touch the mirror, and then draw a parallel line until far enough so that the two lines that you've drawn intersect. And where those two lines intersect, draw another arrow like your O arrow, except this is the I arrow. Okay. So that is your image right there. So your image is formed where the two rays intersect. So you have your object bouncing off the mirror. If I put a screen right here, I could focus this object onto that screen. We're only looking at we're only looking at 1 point really. The other points, centerline points, because these are perpendicular, this is going to be perpendicular as a consequence. So does that make sense? And this is what we would call this a real image, because I could put a screen here. Logistically it's hard to do because your screen would have to be right here, and but theoretically if you put a screen here and you could somehow, this would have to be like a two-way mirror so that you could see through the mirror to get, because otherwise how do you see the image, because you got to get your eyeball in there. It's kind of a catch-22 situation. But if you had, say, a two-way mirror, you could look back here and you would see the object over here with your eyes, and then you'd also see the image of that object projected on this little screen, kind of the same way we have here, but a little logistically a little harder to see. Okay, so that's the first one. Let's now. Well, let me before we move on, let me show you the third thing was I said that if it went to the middle of the mirror and it bounced off at the same angle of incidence as reflection, if I drew this thing exactly to this scale correctly, these two would be the same. Now, of course, I'm just hand sketching it in there, so it doesn't work out. But if everything were geometrically correct, all three of these lines would go through this same point. And so all the light from this point, even though it goes out in all these directions, ultimately they're brought back together at this particular location and concentrated at this point, and therefore all the light is then concentrated and you can see it at that point. Otherwise, if you put the screen anywhere else, the light's going to be all dispersed, and if you're close to this point, the image will be blurry, and if you're far enough away, you won't even recognize the image. Okay, so let me go ahead and let me delete all these lines because we're going to do the next thing. So the question is, what happens if I take this object and I move it here? So what I've done is I've moved it between the center of the mirror and the focal length. Now this thing actually is, I'm going to have to redraw this because you've got one that actually looks good. I just made this up. So let me move. I need to move these together. The center of the mirror actually is the center of the mirror. So I've got this. So I really need to draw this better to scale. But so if I did this again, if I had the object outside of the center of the mirror, I redrew this, it would still end up being between the focal length and the center of the mirror. Now I'm going to move the object to here. So on your drawing, draw this object between the first and second mark. Doesn't matter where, just draw it somewhere between here and just draw an arrow that has small, not too big a length. So this is now where we don't know where the image is yet. Let me just move this out of the way. So you do the same thing. You apply the same rules. So you take the light ray from the tip of the object, you go to the mirror, and you reflect off and go through the focal point. So go ahead and draw that in. So again, your object should be somewhere between the focal point and the center. The first mark is your focal point, the second mark is your center. You go parallel to the axis, bounce off the mirror, go through the focal point. The second ray goes from the object through the focal point to the mirror. So draw a straight line starting here, going through the focal point. You'll extend that to there, and then it bounces off, and the 2 points intersect. Where the 2 points intersect is the end of the image. So now the image is moved, relatively speaking. On your drawing it should, because I changed my scale, it's a little bit different, but now the object is inside the image. You'll notice here the image is bigger than the object. In the one we just finished, the image was smaller than the object. So that tells us something about the magnification. And the image, if the object is between the center and the focal point, then the image has to be outside of the center. If the object is further away than the center point, then the image is between the center and the focal point. So they switch their ranking where they are relative to each other. Now, this is a real image again. If I had a screen here, I could see the object projected on this screen right here. It would be focused. If I had the screen here, it'd be out of focus. If I go back here too far, it's just completely unrecognizable. But if you have it exactly this right distance, the image, all the light rays from the object are going to be concentrated at that particular point. It's going to create an image. Now, when you have an image that's upside down relative to the object, they're called inverted. Okay, so let's go back to the first drawing that you did, which I've already erased, but let me just tell you about that. So next to this first image that you drew here, okay, the one we just finished, not the first one we did, I want you to write a few things. One is, so this is for example one, image is real. Okay. The image is inverted. It's because it's upside down relative to the object. And the image is smaller than the object. So that means the magnification is less than 1. Between 0, well, it's less than 1. Number 2, the image is still real, and the image is still inverted because it's upside down still. But the image is larger than the object. So the magnification is greater than 1. So if the magnification is greater than 1, it's bigger. If magnification is less than 1, it's smaller. So again, here the image is real. This projector, the image is real. It's not, well, it is inverted. So the image inside in the projector is actually upside down. We'll find that out. But this is not I'm just in terms of this description of inverted versus non-inverted. If you take a camera and the film that's in your camera, if you had a film camera, the image in my camera would be flipped upside down. So it's inverted. So sometimes objects, but in a mirror, me looking in a mirror, I'm not inverted. I'm upright. Okay. So if it's the same direction, the object and image are in the same orientation, then they're upright. If they're flipped, then they're inverted. Now, we've looked at the case where the object is outside of the center of the mirror, which is actually the center of the circle. We've looked at the case where the object is between the center and the focal length. In that case, the image is moved out here. The question is, what happens if I move the object inside the focal length of this circular mirror? So let me go ahead and delete those, and that you can turn your paper over and we'll look at that. Whoops, didn't need to do that. So we'll take everything out except this object. We'll stick in here. We're going to draw it inside the focal length. And I'm going to have to move this. You've got space, but I don't have space, so I'm going to move this thing. This is the hard one to understand. Okay. So what you've got is you've got this light ray that comes out parallel to the surface of parallel to the axis of the mirror, and it reflects through the focal point. So that is the same. Now, as far as the one that goes through the focal point, let's do that one. So the problem is the focal point is behind the mirror right here. So if I take the ray that goes from the tip of the object through the focal point, it goes there, and these things never cross except right here at the focal point. So the question is, where the heck do you see an image? Well, what you have to do is you have to project, and also this one, normally in the previous ones, you'll notice that the line that went from the tip of the object through the focal point hit the mirror and bounced off. Well, what you do is you take this, and instead of going this direction, you go this direction. You go the opposite direction, but it's still parallel. And here you show the image reflected backwards off the mirror. And this particular, the one that goes here and bounces back, you take this one and you project that back behind the mirror, like that. And this thing you kind of extend out like that, and these two projections or extensions of these two rays and where they go relative to the mirror. This one that goes, instead of bounces off the mirror and through the focal point, it goes back into the mirror. And this one, instead of bouncing off parallel to the mirror, actually goes back there. What that does, essentially, it creates this image, which I drew the wrong direction. It creates this image behind the screen. So this is my image right there. This is my object. And so because of this, and we'll do a few more of these just to maybe help you out. But what it does is it creates this virtual image behind the screen. Now we have some mirrors that will very clearly demonstrate this fact. It's a spherical mirror, and if you stick your eyeball really close to the mirror, which I'll let everybody do because we got lots of them, is you'll see a magnified version of your eyeball. And it will be, one thing is that you'll notice that the image is in the same orientation as the object. So in this case, to kind of go along with what we did with the previous two examples, in this third case, so there's three cases. In this case, the image is virtual because I can't project this on a screen because this is behind the mirror. So how the heck am I going to put a screen behind a solid mirror? So the image is virtual. The image is upright, which means it's the same orientation as the object. And the image is magnified. So M is greater than 1. It looks bigger. Now, if I drew this thing to scale, this image would actually be further back, but it's just because I'm kind of sketching things. So when we look at our eyeball in that spherical mirror, we'll be able to see it, and we'll also be able to focus it, even though our eyeball is only this far physically from the mirror. But if we take a real object and we put it this far from our eyeball, we can't focus it. But if we look at when we look at our eyeball in that mirror on Wednesday, we'll be able to focus it. And then the question is, how are we able to focus something that is so close to our eyeball? We can't focus. You can't read this close. You can read better than I can. When you get older, you have to hold stuff away from you to be able to keep it in focus. So it's double whammy. And you can explain all of this stuff using these ray diagrams. And for mirrors, the three rules, whatever I did with the rules here, the rules were that light rays parallel to the mirror axis reflect through the focus or the focal point of the mirror. The second one is that light rays that pass through the focal point reflect parallel to the mirror axis. And the final one, which we don't have to use but also applies, is the light rays that bounce off of the center of the mirror, which is where the axis is, have equal angles relative to the mirror axis. And where those light rays bounce off and cross, the paths cross, that's where the image is focused. And the ray diagrams are able to tell us what is the relationship between the size of the object in the image, the relative orientation of the object in the image, and the magnification. And so ray diagrams do that, but also there is this equation for the mirror. And so you can do it mathematically as well. And I will define what these things are just a second. So P is the distance from the object to the mirror. And we're talking about, all of these are based upon the axis of the mirror. Q is the distance from the image to the mirror. And R is the radius of the spherical mirror. It also turns out that the focal length is equal to the radius divided by 2. And so if you look at your drawing here, there's the two marks. The leftmost mark here is the center. If I drew a circle, the center of the circle would be there, and the distance from that center to the circle is the radius. If you take half of the radius, you can see that second mark is halfway between the center and the surface of the mirror. That's the focal point. So for spherical mirrors, the focal point is always the radius of the mirror divided by 2. So another way that you could write this mirror equation is in terms of focal length. So this is also 1 over P plus 1 over Q is equal to 1 over F instead of 2 over R, because F is R over 2. So either one of those works. And what we'd find out is if P is greater than R, that's the first case that we did, then Q is going to be somewhere between the focal length and the radius. That was the first case. The second case, P was between Q and F. And the third case was the P was less than F. And those three combinations will give you the right answers as far as the location of the object and image and given the focal length or the radius of the mirror. So we'll continue this on Wednesday. We'll do some stuff in the lab, but we'll also continue to draw these things. So I've got more sheets that I'll hand out on Wednesday, and that'll be it. Just keep those for right now, but because we got one more